G'day, I'm Phil from the Civil Aviation Historical Society and Airways Museum, and I'm just going to give you a few words about the exhibits in our museum. The first thing we've got over here is a recreation of one of the first air radio stations in Australia. In the early days of flying, aeroplanes didn't carry radio, and there were a couple of accidents, including a well-known one up in the Lamington Plateau in Queensland where an aircraft crashed in bad weather, and they realised that there was no way of communicating with aircraft in flight to pass on weather information and so forth. So in 1934 the Department of Civil Aviation required all passenger carrying aircraft to be fitted with radio, and the ground stations they communicated with were run by Amalgamated Wireless Australasia. They were shipping radio stations, coastal radio stations set up for communications with coastal shipping, and the aeroplanes communicated with those stations, but that really wasn't a practical long-term solution. From 1938, the Department of Civil Aviation contracted with Amalgamated Wireless Australasia to set up a series of 12 air radio stations throughout Australia on the main air routes, which in those days were basically up the east coast of Australia and into New Guinea. The air radio stations were constructed along standard lines. They had a standard set of equipment and standard buildings that they could put up as a package with slight variations in throughout along the air routes, I should say. This diorama recreates the air radio station at Cloncurry. What we had on in the left-hand side of the operator was two racks of audio equipment. The middle rack with its telephone the device next to the phone was called a Strowger relay. It was an early form of remote control. The HF transmitters were located about a mile away from the air radio station so that they wouldn't interfere with the receivers, and the operator could actually telephone the transmitter and change the frequency of the transmitter by remote control. And that's what that telephone is. Next to the audio racks, we've got three HF receivers that were mounted inside the air radio room, and the operator could tune these to different frequencies. One of them would have been a ground-to-ground for ground-to-ground communications, so that he could communicate with the next air radio stations along the route, and the other ones for communications with aircraft. On the desk, on the left-hand side of the desk, the air radio operator had a device called a Bellini-Tosi direction finder, medium frequency direction finder, and using the dial at the bottom left of that console, he could tune the antenna system for the direction finder to get a bearing of the aircraft from the ground station. And that bearing that he obtained from the aircraft would be then transmitted back to the aircraft, and that's how they would find their way. Of course, there were no radio navigation beacons in those days, so if you were flying in cloud, that would be your only way of fixing your position. You could get bearings from several ground stations. The bearings would give you lines of position. If you plotted those on a map, you could tell roughly where you were, but it wasn't particularly an accurate system. Okay, one thing that's important to remember in the early days of flying, that aircraft radios were big pieces of equipment, and not only that, but you needed a specially trained operator who could do Morse code to operate it. This is a typical radio equipment set from a US Air Force bomber during the war, but it illustrates the size of the radio equipment of the day. Obviously, only large aeroplanes could carry radio equipment like this, and so small aeroplanes didn't have any radio or any means of communicating with the ground. After the original 12 air radio stations were established, the war came along in 1939. In 1941, the Japanese ended the war, and Australia became heavily involved in fighting throughout the Pacific. Of course, there was a lot of air traffic associated with that, and the need to expand the air radio system to cater for all that increased traffic meant that a new series of air radio stations had to be set up, particularly on the Adelaide to Darwin air route, which was quite vital, and also up through Western Australia. Because of the war, equipment was in short supply, so they couldn't use the standard pattern air radio stations that they'd used pre-war because that wasn't available. So what they did was they just pressed into service anything that they could get their hands on, including a lot of aircraft radio equipment, which was converted for use in the ground. And this is a recreation of the air radio station at Daley Waters in 1939. It was located in the post office. You can see there's a photograph on the wall to the right there. It was an unlined tin building. You can imagine how hot that would have been in Daley Waters in summer. And yeah, the operator or operators had to maintain a watch for all notified aircraft movements. They were basically on duty 24 hours a day, 7 days a week, and they just opened the station for notified movements, which could be at any time of day. And of course they were pretty isolated back then because basically the aeroplane was the only communication with the outside world, and often the airlines would bring fresh food with them for the air radio operators. It was a pretty rough sort of existence, but it was the war and people had to do what they had to do. After the war, materials and equipment were still in short supply, so this sort of equipment lasted in service right through into the late 1940s. Later on they started putting in some more modern equipment in racks rather than just desk mounted equipment, but it was still largely war surplus equipment. From the 1950s onwards, the Department of Civil Aviation was able to start building purpose-built equipment again for its air radio stations, and air radio became flight service in the late 1940s. The purpose of flight service was to provide traffic information to aircraft that were outside of controlled airspace, and also the flight service operators, because they lived in the communities that they served, they had a good knowledge of the local airstrips and the local conditions, and they were able to pass that on to pilots as well. This console is a typical purpose-built piece of equipment. This was used in Mildura flight service. It was constructed in 1969 and remained in service till 1984. Had two operating positions. The main radio equipment was remote instead of being inside the building with the operator. Now we had VHF radio for communication over shorter distances, but still had HF radio as well. All of that was remotely located. In the centre of the console we've got a number of instruments, wind speed and direction, the temperature and the altimeter setting indicator or QNH indicator. In the drawer the operator also had a CR6 HF radio that was a backup, so if everything else failed he could use his backup radio, and they used to often tune that to the footy or the cricket scores. What we can see from this map, this is a console map from the Mildura Flight Service console. These green lines show the flight information areas, so each of these areas was the responsibility of a different flight service unit. Now in the days that we're talking about, you couldn't remote communications. The operator had to be where the radio equipment was. That's why we had air radio and flight service units all over the country, including Mildura. And the Mildura area was responsible for, Mildura Flight Service was responsible for this area here. Later on we'll see on a later console how the areas were able to be greatly expanded, and of course meant a reduction in the number of flight service units that were required. One of the features of every flight service unit around Australia, and also of air traffic control units at the major centres, was a briefing counter like this. So pilots could come into the flight service unit and talk to a flight service officer or an air traffic controller in the bigger places, and they would be able to get their NOTAMs, weather information and so on. They would be able to submit a flight plan, which in those days had to be approved by the flight service officer or the air traffic controller before they could go out and go flying. This console here came from Charleville, was recovered from underneath the flight service station some years after it closed in the early 1990s, when the then Air Services Australia or Civil Aviation Authority withdrew face-to-face briefing services. So now briefing is all entirely done over the telephone or by fax or by the internet. From the late 1980s, satellite communication technology meant that communications could be remoted away from remote locations back to the major centres. And so the Civil Aviation Authority embarked on a program of consolidating all of its outstation units, particularly the flight service units, into big centres within the capital cities. So units like the Mildura Flight Service were closed down and their function was taken on within the centre. To do that, they used a different type of console which enabled the flight service officer to look after a much larger bit of airspace. So this belongs to the old FS15 position in Melbourne Centre, in the Melbourne Flight Service Centre that is. And that was responsible not only for the old Mildura area that we looked at on the other console, but also most of this area through northern Victoria and right over into South Australia. It was all the responsibility of this one console. So you could see that one person could do the job that previously took a number of other people to do. So it represented quite a saving in manpower. Okay, these type of consoles were used in the centres from the mid-1990s until the year 2000, when flight service finished and its functions became part of air traffic control. This console remains set up exactly as it was when the flight service officers walked out of the centre for the very last time in 2000. On the console down the bottom here we have, well, firstly on the desktop we have a number of different sheets of information that were things that the flight service officer would want to refer to quickly, including frequencies and so on and so forth. These buttons along the bottom here were all different intercom lines to various units around the countryside, and these little switches here are the press to talk switches, so the flight service officer would have his headset plugged into here and talk to the aircraft by pressing that. Along the top of the console, these buttons here are all the frequency controls, so the flight service officer would be responsible for a number of frequencies, 10 or more perhaps, including HF, which was operated from these consoles, and these buttons enable him to select various transmitters and receivers. Across the top here we also have a weather radar display. In the middle we've got our strip display, so each flight has a strip which has various information on it, including the aircraft's call sign, its type, where it's going from and to, and reporting points along the route with estimates for those points and the level that the aircraft would be at. And these are how the flight service officer would keep track of where the aircraft was. And each strip would be placed under a particular bay relevant to the area in which the aircraft was operating at the time. So for example, this one is Nil, Warwick, Nabil and Horsham. So any aircraft operating in that area would all go under that designator, and then the flight service officer could see which aircraft were likely to be in conflict with each other and then use that to determine whether he had to give traffic information or not. Now, this magnificent piece of equipment was an HF radio transmitter called a J2876. And this is the HF radio transmitter that is the counterpart of that first air radio diorama that we looked at. So this was the equipment that they set up in the 12 standard air radio stations in 1938. And how they ever got it out to places like Cloncurry and whatnot back in those days is beyond me, but anyway, they did. It was built in Australia, it was built to last, and these transmitters were used right up into the 1980s for converted from manual Morse code to high-speed teletype Morse code. They had 4 channels, 3 high frequency and 1 medium frequency channel. Okay, this J2876 was a 4-channel radio transmitter. It had 3 high frequency channels and 1 medium frequency channel. And this particular one's been set up so that its MF channel operates as an NDB or a non-directional radio beacon, which didn't actually make an appearance in Australia till the wartime years. But these, as I said, were long-lasting bits of equipment, typically installed in remote locations, maintained by the operators on site. Right, in this crate is a typical valve that was used in the big HF radios that the department operated for many years. They were transported around the countryside in these specially sprung crates because of course they were quite delicate, and you can imagine that once upon a time DCA would have had warehouses full of these particular crates. Enormous bits of equipment now, and the function of this would be smaller than the spec on the head of a pin these days on a printed circuit somewhere. In the 1960s really, HF radio technology began to change with the replacement of valves with transistorised equipment, and that enabled what formerly would have taken a whole cabinet on its own to be miniaturised into something that could fit into an electronic rack, a standard electronics rack, like this piece of equipment. What's often not realised with aviation is that behind the aeroplanes flying from A to B is a worldwide network of ground stations of air traffic control or flight services we used to have, and those ground stations need to communicate about the aircraft that are flying from one station to the next. So there's a worldwide communications network called the Aeronautical Fixed Telecommunications Network that spans the globe and carries messages about aircraft movements. And up until relatively recently, probably 25, 30 years ago, a lot of the message traffic went by high-speed Morse code that was generated by machine. And this equipment here is some of the early equipment from the 1950s, but used quite up until probably the 1970s, that enabled that traffic to be sent around the world. So on the left we've got a teletypewriter. So that's how the messages were received and printed out on a piece of paper. In the middle is a tape perforator. So the operator would type their message out on the perforator, which would punch holes in a paper tape in special characters that related to whatever the message was. And that would be sent into or fed into a tape reader, and that tape reader would convert the message from the paper tape into Morse code. That would be sent at high speed using HF radios for communication, particularly with overseas stations, because of course there were no satellites in the early days and certainly no landlines to a lot of those places. So it was all done by HF radio. And at the other end, the HF radio would, or the receiver would receive the signal, will be sent to a teletypewriter, and that would decode the incoming signal and print it out as a legible message on a piece of paper. In the 1970s, to control the messages that went around the AF10, we started to see automated equipment being brought in for message switching, which was previously done manually by various operators. And this equipment is some message switching gear dating from that period, quite early, and we're starting to see the introduction of printed circuit boards into messaging equipment. By 1936, the traffic at the larger aerodromes in Australia like Mascot, Archerfield, Essendon and Barrafield had become reasonably heavy, especially on weekends when there was a lot of popular flying. And so the Department of Civil Aviation decided that they needed to put in some air traffic control basically. So they employed the first air traffic controllers. In those days they operated out of towers like this one. This is the first tower at Mascot Airport in Sydney. They were simple glass boxes built on top of the aero clubs at those locations. The controller had no radio, so he used to communicate with the pilots of the aircraft in a number of ways, but primarily, totally visually. He had a mast outside his office where he could hoist some cane balls, painted different colours. These were derived from the old marine type of signalling, and depending on which coloured balls you had in which combination, it meant certain things like fly circuits in a standard direction, or the field was unserviceable or whatever. The air traffic controller also had a signal square outside the front of his office where he could lay out certain signals, bearing in mind the aerodromes were all over grass fields in those days. So one of the things he would lay out was what they called the landing tee, which showed pilots which direction the wind was coming from and in which direction they should be landing on the all-over field. As well as that, the air traffic controller had a number of other devices at hand. Here's a picture. This one's from the 1940s, we think from Mascot Tower, a later tower than the one we saw there. Here's the controller with his tools of trade, the Elvis signalling lamp, which you could use to flash various signals at aircraft, and also on the bench here, just visible, is a Vabre pistol. And it was a sad day for ATC when they got rid of the Vabre pistol. So here's the Elvis signalling lamp. This was actually made for the Air Force during the war, but DCA used many of them during and after the war. Had a little trigger here so that the air traffic controller could signal to the aircraft, and a little sight so that he could line up accurately. You could put a different coloured lens on the front of the lamp depending on what the purpose of your signal was. And what we also have in every tower today, every control tower, we still have a large version of the signalling lamp. Don't use it very often anymore, only used for emergencies these days, but it was used for communicating with light aircraft coming into places like Essendon right up into the 1950s. Even though VHF radio came in the 40s, they were still big and heavy pieces of equipment, and small aeroplanes like Tiger Moths and things of the day couldn't really be fitted with radio equipment. Now, the first control towers, as I said, were built pre-war, and they were really just add-ons to existing buildings. During the war and then after the war, the first purpose-built control towers came to be constructed. And in those control towers came the first purpose-built consoles like this one. This tower console dates from the 1950s. We've got on the fascia, we've got the instruments for wind, speed, direction, QNH and so on. And we've got on the face of it, or on the bed of the console, we've got room for various strips. So once again, each strip was raised for each flight, showing the call sign of the aircraft type, where it was coming from and to, and the time, in this case, either time of arrival or time of departure. On this side of the console, this device here we've got is called a semi-automatic altitude assignment board. And that was an invention that was necessary because of increasing air traffic in the 1950s. In those days there was no radar control, and so all aeroplanes were fed in using what we call procedural separation standards. That means they were kept apart by either a distance or a level, so assigned different levels. Obviously, with all the aircraft coming inbound to an aerodrome such as Essendon when it was bad weather, all the aircraft would come in, they would all converge on the aerodrome, so they would all have to be stacked up vertically. So that meant you had aeroplanes holding at different levels over the aerodrome or over the approach beacons. That meant that there was a lot of coordination between the arrivals controller, who was feeding the traffic into the holding patterns, and the tower controller, who was feeding them out at the bottom to do instrument approaches. To overcome that requirement for a lot of coordination, the semi-automatic altitude assignment board was invented, and that enabled the tower controller and the arrivals controller to coordinate levels between each other without actually having to ring up and talk to each other using a system of coloured lights here. So as the tower controller cleared aircraft to descend in the holding pattern, you would move the strip down and pull up the plunger where the aircraft, when the aircraft reported at the new level, you would pull up the plungers for the levels above, and that would show a green light on the arrivals controller's console, and it would mean that he could assign the next aircraft in the approach sequence to that level. So as long as both parties knew the order of arrival, they could coordinate the assignment of levels without having to actually talk to each other. And also on this console we've got these microphones. These were an Australian invention. Very handy, even though they look a bit odd, because they're very ergonomically favourable. And if you look closely at them, you can understand why they were known as penis phones. Straight after the war, the Department of Civil Aviation recognised that radar, which had really come to the fore during the war, had a lot of application for civil aviation. And so they started doing some experiments with it. The first radar trials were done here at Essendon Airport using a military lightweight air warning radar, and that was housed in a tent located on the boundary of the airport. It wasn't a really very practical thing for a number of reasons, but it gave the department its first experience with radar. In the 1950s and 60s, 1960s really, the department had done a series of experiments with other radars, and they culminated with the first sort of proper air traffic control radar, which was this unit here, made by COSA. It had a range of 40 miles, which in the days of DC-4s and things was acceptable, but when the jets came in, became a bit limiting. The operator used to live in a little cubby house in the back of the tower at Essendon. This is a picture of Essendon Tower from about 1962, we think. And you can see the operator up the back here in his little cubby house. The principal separation was still done procedurally, but if they had a particular separation problem that they wanted radar to sort out, they would assign the responsibility to the radar controller. This is a typical later tower console, a more modern one dating from the 1970s, but it's still pretty typical of the consoles that you find in a control tower today. This one came from Alice Springs. It was purely a procedural console, that is, there was no radar there. And you had it laid out basically with an aerodrome controller at the right hand side and an approach controller in the middle. And at the far end on the left here we've got all the controls for the airport lighting and the navigation aids and so on. And this device here, you still see these on many air traffic control units. They are a great thing. It's called an Ericaphone, very ergonomic once again. During the war, the increasing amount of air traffic led DCA to think that not only did they need to control traffic around the aerodromes with the control tower, but they needed to control traffic en route as well. And to do that, they first established air traffic control centres that kept track of aircraft movements using a huge blackboard. Okay, air traffic control is a bit like an iceberg. If you ask somebody about air traffic control, what they know about it, most people think of the control tower, but in fact most of the activity goes on within the air traffic control centres. The tower really only looks after the immediate area around its particular airport. And the first area control centres were established just after the war, when DCA realised that they needed to provide some control for traffic on the main trunk air routes. Originally, the traffic was kept track of by the air traffic controllers using a giant blackboard on which they wrote position reports from the aircraft. And that was called the air traffic pattern board. And the communications with the aircraft were done through air radio, so it was all third-party communications. They had no direct contact with the aircraft themselves. It was a pretty cumbersome system and soon came to the limit of its capacity. So they needed another way around it. And what they came up with was this device here, which is called a Rodanoscope. It was invented by a chap called Norman Rodani. He was a flight checking officer, as they called air traffic controllers in those days. And he was formerly the chief pilot of Adastra Airways. They'd been engaged on a lot of photo survey work during the war, and Norm Rodani's health had failed because of all the high altitude flying, and he wasn't able to continue flying, so he became an air traffic controller, as was the way in those days. Anyway, Norm Rodani invented this device. Basically it's a giant circular slide rule, and the flight checking officer would mark the position reports of aircraft on it in Chinograph pencil as they were received from air radio, and by rotating the disc in real time he would be able to tell whether aircraft or what time of passing he would have for two aircraft that were flying opposite direction, or whether he had 10 minutes between aircraft proceeding in the same direction, which was the basic separation standard, or whatever the particular separation requirement was. It was quite a good invention for its day, and Norm Rodoni actually won £400 in prize money from the War Inventions Committee, but it soon also reached the end of its limitations, or it reached its capacity. Okay, to replace the Rodanoscope, DCA did a search around the world for better systems, and they came up with the Flight Progress Board. This had been first used in the United States, and we adapted it here for en route control, which is control basically outside of the terminals where the major airports are. The basic principle of the Flight Progress Board was that the controller had a strip for each aircraft within his area of responsibility. The console, I should say, was divided up into a number of bays, each with a bay designator representing a particular geographical location within that sector of airspace. A strip for each aircraft would be placed under the appropriate bay designator, so in this case this one's for Wagga, this one's for Albury, so if you was going via Wagga you would have a strip under the Wagga designator. By comparing all the strips within that bay you could tell were the aircraft at the same level. If they were at the same level, did you have 10 minutes between them, which was the basic longitudinal standard, and later on when we got DME, did you have a DME standard or whatever the thing might be. We had buff coloured strips for aircraft flying in one direction and blue coloured strips for aircraft flying in the other direction. So that meant if you had two buffs, for example, you had two aircraft flying the same direction. If you had a buff and a blue, then you had an opposite direction conflict. It was a very, very good system, and it served us up until the year 2000 when air traffic control moved into the computerised TAT system. It had its limitations. It had limits as far as how much traffic you could display, and it also required the controller to keep the picture in his head a lot more than with our air situation displays today. But as I said, it was a very good and user-friendly system overall. These consoles date from the 1950s. They're the very earliest style of flight progress board we used in Australia. The original trials were done in 1946. Later on, flight progress boards became a lot more fancy than these consoles, but the basic principle still continued through until 2000. On this console here, this was the arrivals console, and this had the semi-automatic altitude assignment board that corresponded with the semi-automatic altitude assignment board in the tower. So the controller operating the arrivals console would be arranging all inbound aircraft into vertical stacks when the weather was bad, and they would go into a holding pattern. His job was to feed them into those holding patterns, and then the tower controller would peel them out of the pattern to do their approach and land. As we mentioned earlier, DCA had been doing experiments with radar for quite a while after the end of the Second World War, and by the 1960s they were ready to go into radar properly for en route control as well as for local control around the aerodrome. Starting in 1962, the department bought a number of these systems. This is called the Bright Display System, made by Thomson CSF in France, and this was our first, what you might call, proper long-range radar system. These two consoles here are approach consoles, and for the first time we had radar approach and departures control, and that's how we run our modern system today at our capital city airports. This dual console was to an approach and departures position. They were called approach and departures, but they actually generally focused on that, but they could interchange aircraft, so departures might do approaches in certain circumstances and vice versa. This device on top of the console was a thing called TAST, or Terminal Area Severe Turbulence. It was a TV picture basically relayed from the Bureau of Meteorology, where they drew a diagram of what their weather radar was showing them and then televised it to the control centre. It was a pretty cumbersome thing. It was introduced following the Viscount crash into Botany Bay in the early 60s to try and provide some sort of weather information in the centres, and I suppose it was better than nothing, but it was pretty rough. This is the display, or a picture of the display from the bright display radar system. You can see all those lines on here are various airspace divisions and air routes. This is a picture of Melbourne, so this is the Melbourne control zone here. Melbourne Airport there, Essendon there. That's Point Cook, that's Laverton, that's Point Cook. Avalon down here and Moorabbin here. All those little marks here, these light coloured marks, are aircraft. Down here in the Moorabbin training area, we've got these little slashes. These are aircraft operating without a transponder. In the early days of the bright radar system, nobody had transponders, so it was all what we call primary radar. That's like the old Battle of Britain, where the radar sends out a big burst of energy from the ground, and some of that's reflected back to the radar receiver. As you can see, the picture is very sort of fuzzy and not all that clear. From the early 1970s, transponders were introduced and secondary surveillance radar came into use. Secondary surveillance radar, or SSR, is a different type of radar system that relies on a transponder, a transceiver, and a transmitter and receiver within the aircraft. The radar system sends out a pulse of energy that's received by the transponder in the aircraft, which transmits information back to the ground station. SSR has a couple of advantages. One is that very much less power is required to be radiated because the aircraft's sending a signal back to the ground. And also, because the transponder is sending a signal back, that signal can contain useful information, such as a code that identifies the aircraft and also the aircraft's level. On our display here, we can see in the early days of the bright display system and SSR, we only were able to use what they call non-discrete codes. That means that you could assign a code to an aircraft that could be used by any number of aircraft of that category. So for example, these rectangles up here are aircraft squawking the code for heavy aircraft. These little circles here are aircraft squawking the code for domestic aircraft. So we don't know which actual aircraft that is, just that it's squawking that code for that category of aircraft. In order to keep track of which aircraft was which, the controller had to use a thing called a shrimp boat. This was the shrimp boat. It's a little piece of perspex, and the controller would write the call sign of the aircraft on this piece of perspex with a chinograph pencil. It would moisten the piece of perspex, and you could stick it onto the radar screen, and it would hold on there using capillary action. Now that was all very well, but of course the aeroplane blips moved around on the screen, so as the blips moved around, the controller would have to keep moving his shrimp boats along. And you can see that it didn't take much for all the shrimp boats to fall off, and you would have to start again by identifying which aircraft was which. So it was a pretty crude system, but it seemed to work. In the late 1980s, advances in computer technology meant that the air traffic control systems could be computerised, and we switched to a new type of radar display system called ACT cards, and later on it was called OzCats, but it was the same system essentially. What this did, instead of having basically the raw radar picture presented as the bright display system did, the OzCats system or ACT card system, all the data was fed to a radar data processor, and then that would then draw a picture on the controller's screen. And here's a picture of what the display looked like. Same as before, this is the Melbourne control zone. The display was very, very finely drawn. It was a lovely piece of equipment to work with once they sorted out some teething troubles. This is what I cut my teeth on actually. And because it was all filtered through a computer, what that meant was that for the first time we could allocate discrete codes to aircraft, which meant an individual code for a particular aircraft that identified that individual aeroplane. And the computer, we could tell it what code belonged to which aircraft, and it could put a label onto the track, such as we've got here, that told the controller what the call sign was, so we didn't have to have shrimp boats anymore. Also, for the first time we were able to get the level of the aircraft from its Mode C transponder, and so the controller then didn't have to keep asking aircraft, as they did in the previous system. They had to report present level, report present level, report present level. Didn't have to do that anymore because you could read it directly off the screen automatically. So that saved a lot of communication time. The other thing that we're able to get from this was the ground speed which the radar data processor calculated automatically. One other important time saver in this system was it introduced for the first time the concept of what we call jurisdiction. That meant the computer knew which aircraft belonged to which controller, and it could assign jurisdiction to that controller. In the previous systems, when the aircraft got to the edge of your airspace and you wanted to hand it off to the next controller, you had to ring them up on the intercom line. You had a little arrow that you could put up on their screen and wave it about, and you had to ring them and say, that is Alpha Bravo Charlie 7000, and he would read back, accept Alpha Bravo Charlie 7000, and then you could tell him Alpha Bravo Charlie to call the next controller. With the AusCat system, you could do all of that silently. It's called silent handoff. Using this rolling ball and the designator, you could designate the particular aircraft that you wanted to hand off. You had one button to push, depending on which sector you wanted to hand it off to. It would cause the track to flash on the receiving controller's screen, which was the signal that you were trying to hand it off. He would push one button, the accept button, here, and that told the computer, okay, I've got it now. That would cause it to flash on your screen, and that was a signal for you to tell Alpha Bravo Charlie to call the next controller. So where previously we had a lot of coordination at handoffs, in this system we could do away with that and do it all silently. So it was a much more efficient system in that respect. This system continued up in use up until about 2001, when the final ATC units transitioned to the new TAT system that we use today, or Eurocat system. In the early days of flying, there were no radio navigation beacons. We talked about direction finding before as the only way that pilots could find their position when they were flying in cloud. But there were shortcomings with that system, and DCA realised early on that a system of radio beacons was necessary. They did a worldwide tour in the early 1930s or mid-1930s to see if they could find a system that would be suitable for Australia. And what they decided on was to adapt the German Lorenz system, which operated in the 33 megacycle frequency. It was originally designed as a blind landing system, blind approach system, but our engineers adapted it as an en route navigation system. It was a beacon that had two courses. We can see from this map here, these show the Lorenz beacons. This one's at Launceston. Here's the Melbourne one. The Melbourne one had one course pointing down towards Launceston and one course pointing towards Adelaide. So you could fly inbound or outbound on that course of the beacon. If you were going to Sydney, you had to get airborne and pick up the Mangalore beacon and fly on that. Likewise, in Hobart, we had one leg pointing to Launceston, but we got one leg pointing off down towards the South Pole, which obviously nobody would have ever used, except they could have used it for approaches at Hobart. But it was a relatively inflexible system, but it was the best we had. It had a range of about 80 miles, so there was a gap between beacons typically that you would have to fly on dead reckoning until you came within range of the next beacon. These beacons operated from 1938 through till 1953. It's interesting to think that the Lorenz beacon system was the first network of what we would today call VHF radio beacons that was in service anywhere in the world, and that was Australia leading the world in those days. Okay. The Lorenz system had its disadvantages, one of which was that the frequency they used, the signals weren't always all that clear. They got a lot of reflections. And after the war, DCA introduced the American VAR system, or Visual Aural Range. The VAR had the advantage of having 4 courses as opposed to the 2 courses of the Lorenz system. The VAR was introduced in 1953, and beacons were still in operation into the early 1980s. From the early 1960s, the VAR began to be supplanted by another type of radio beacon, which we still have today, called the VOR, or VHF Omnidirectional Radio Range. The VOR was a much more flexible radio beacon because it offered 360 courses as opposed to the 4 courses of the VAR. The difficulty with the VOR for Australia was that the beacons were quite expensive, and so they were only installed along the major air routes and at the biggest airports. And the non-directional beacon, or NDB, remains Australia's most widely used radio navigation beacon. They first came to Australia during the Second World War, and they were known as homers in those days, later on called NDBs. They're basically a simple radio transmitter that radiates a signal equally in all directions, hence non-directional, and the aircraft carries a direction finding equipment, usually an automatic direction finder or ADF today, that allows the pilot to home on the beacon, hence the name Homer. This NDB here is a typical beacon from the 60s and 70s. They're found at a lot of country aerodromes, kept in a little shelter like this. This one's got some transistorised equipment. Previously they would have been valve operated, and today of course they're all constructed using printed circuit boards. During the war, Second World War that is, radar technology made some big advances. One of the devices that was invented was a thing called Rebecca Eureka. This was a system that was invented primarily to allow the British aircraft to drop supplies to bands of Marquis operating in France and the occupied territories. Of course, there were no lights, no way to navigate at night in those days, and it was difficult to find these isolated bands of resistance fighters to accurately drop the supplies. So what they had was this Rebecca Eureka equipment. The Eureka was basically a transponder that was the size of a suitcase that they could take to France with their agents. They would take it out to the field where they were going to receive the supplies, and the aircraft would come along using its Rebecca system, would be able to range on the transponder, the ground transponder. So it would send a signal out to the transponder, which would reply using the time that it took to travel from A to B, from the aircraft to the ground and back again. They could work out the distance that the transponder was away from the aircraft, and they could use that to home in on the Eureka transponder, and they could find the agents, drop their supplies and so on. Now after the war, DCA realised that that idea could be adapted to civil air traffic, and one of the problems up till then was that we had radio beacons that gave the pilot a track to fly, so you gave him left and right guidance, but until you actually flew over the beacon you couldn't fix your position along track. For air traffic control in particular, with more congested air routes, that was a problem because all they could do was measure the time between successive aircraft crossing radio beacons, which wasn't, it was a fairly inflexible way of doing air traffic control. So to enable a pilot to fix his position continuously along track, DCA and the CSIRO worked on the idea of what became known as DME, or distance measuring equipment. And this piece of equipment here is one of the experimental DME beacons that they developed. One of the very earliest things from about 1950, this one dates. And the basic idea of DME is that you can measure the distance continuously between the aircraft and the ground station. This is a typical production DME equipment. There would have been 2 of these units housed in a hut together. This was made by AWA in Australia. This was the Australian Dme System, which operated from the early 1950s through until the mid-1990s when the Australian Dme System was shut down. Australia was the first country in the world to have a network of operating DME beacons, and it was a great advance for its day. Unfortunately, the Australian system was overtaken in time by the American system, which became the de facto international system because the American military forces basically spread their DME beacons around the world for free, and so the Australian system became isolated really just to Australia. But as I said, Australia was the first country in the world to have a network of operating DME beacons. This is the antenna system for the AWA Australian DME beacon. These would have been mounted on a pole 10 metres or so high. With the early DME equipment, because we were still in the era of valve technology, it was very bulky equipment, so only big aircraft were equipped with DME in the early days. The meter for the DME was an analogue meter which read on a dial the distance from the beacon. The pilot could switch to different range scales, and also using a different switching again could measure ground speed, which was just the differential of the distance. So this equipment here is the Van 3 Interrogator. This was the first airborne DME equipment. In later years the equipment became miniaturised as first transistors and then printed circuits came into use, and we changed from analogue displays to digital displays, and now of course everything's on the EFIS display. This cabinet doesn't look much on its own, but it's quite an important piece of equipment. This is the Microwave Landing System, or MLS, that was invented in Australia. Originally the idea was the ILS, or Instrument Landing System, which is common throughout the world, dates from the Second World War, and it's very susceptible to interference. It requires a lot of work to keep the signals being radiated properly, and they're quite expensive to install, plus they're inflexible because they only provide for one approach path. So the idea was to invent a system that could be a lot more flexible and a lot more reliable and cheaper to install than ILS, and the MLS, or Microwave Landing System, was Australia's answer. It used a scanning beam, which meant that the antenna would scan a volume of airspace and pick up the aircraft within that volume, and it could accurately measure the aircraft's position from the ground. By various devious means, the aircraft could be made aware of that position, and the aircraft would be able to fly accurate approaches in very bad weather, and also it offered the possibility of curved approaches or multiple approach paths, which would have given a lot more flexibility. The Australian MLS, after a lot of competition, was selected as the world standard for the future instrument approach system. However, the introduction of satellite technology and GPS in particular meant that MLS never really got off the ground. It is used in some parts of the world for very specialised applications where they needed the MLS capabilities, but generally speaking the airlines have chosen to stick with ILS until hopefully GPS will provide the same sort of capability in a different form. As well as maintaining a network of radio navigation beacons, each beacon has to be regularly flight tested to make sure that it's continuing to radiate properly, and so the Department of Civil Aviation and its successors have had to maintain aircraft for that specialised task of calibrating radio navigation aids. In the early 1970s, the department acquired 3 Fokker F-28 aircraft which were fitted out for Airways calibration, and this is the console from one of them, Alpha Tango Delta, and this is where the survey operators would have sat to do their work, back in the cabin of the aircraft. The way the system worked was using this device over here called the optical tracker. What they would do was they'd send a chap out to the nav aid to be surveyed, and he would set the optical tracker up at a pre-surveyed point. The aircraft had a light on its nose, and the operator would focus the TV camera on the light, which would electronically lock onto that light. Using a VHF radio data link, the accurate theodolite within the optical tracker would track the progress of the aircraft, which was flying a particular, say, inbound course of a VOR or down the ILS, and would transmit the information back to the aircraft, where the surveyors in the aircraft could compare where the aircraft actually was to where it should have been and work out whether the nav aid was radiating correctly. One of the problems that was recognised early on was for aircraft landing at night, or aircraft doing instrument approaches in bad weather, transitioning from flying on instruments to the last visual segment of the landing, was how to judge glide path correctly. And there are a number of quite bad accidents worldwide where aircraft undershot or overshot on the approach, particularly at night. DCA tackled this problem in conjunction with the Aeronautical Research Labs, and they came up with the idea of a system which later became called the T-VASI, or T-Visual Approach Slope Indicator System. This is a light box from the T-VASI system. There are 20 odd of these within a complete system laid out on the aerodrome near the touchdown point on the runway. The system shows a series of lights. You can see on this diagram over here. When the pilot is flying the correct approach slope, all he sees are two horizontal bars of lights on either side of the runway threshold. As long as he's flying the correct slope, that's all he sees. If he goes above the correct glide slope, he starts to see an inverted T of lights, and the higher he goes, the longer the stem of the T becomes. So if he sees the inverted T coming up, the pilot knows he's got to fly down a bit to regain the glide slope. Similarly, if he undershoots the glide slope, he starts to see a T forming, and the T shows the pilot that he has to fly up. If the pilot gets dangerously low, the white lights in the system change to red as a warning. It's a very, very accurate system. The first trials were done in 1956, and in 1960 it was adopted internationally as a standard for approach lighting, approach slope guidance, that is. The first production units were installed at Hobart in 1965. It's, as I said, one of the most accurate of the systems available. It certainly was more accurate than any of the other systems available at the time, although it's starting to be replaced by PAPI, or the Precision Approach Path Indicator system, throughout Australia now. One of the reasons being that it's quite an expensive thing to install compared with the PAPI system. One of the essential features of any airport is its lighting systems, and the Department of Civil Aviation was heavily involved in that in the days when it used to run airports. There's a wide range of lights, and they're all mostly specialised in design because of the application to which they're put. For example, these taxiway lights here, designed to be as flush as possible so they can be taxied over if necessary, and they have a very, very thick lens to prevent them being crushed. Similarly, we've got runway threshold lights here designed to be mounted flush with the runway, or nearly flush, so they can be run over. These are runway side lights, different styles of side lights. Down here we've got high intensity approach lights. These are designed to lead the pilot to the runway in bad weather. And also we've got portable lighting. So a lot of aerodromes, especially country airports, had portable kerosene lighting, kerosene lamps, so that they could put out a flare path at night. We've got batteries for, that's a transformer for approach lights. This is a different style of electric portable lighting. This is an apron floodlight. There's still lights like this in service at Moorabbin. And also, no airport would be without its rotating beacon, which was used to guide the pilot of an aircraft visually to the airport in bad weather. So that really concludes our tour of the Airways Museum, and I hope you've enjoyed listening to it. Shut up.